Good morning, everyone. My name is Laura Titolo, and I'm a researcher at the National Institute of Aerospace. In this talk, I'm going to talk about our work, a compositional proof framework for FRETish requirements, which is a joint work with Esther Conrad, Dimitra Giannakopoulou, Thomas Pressburger, and Aaron Dattel from NASA. So, FRETish is a structured natural language that was developed at NASA, which provides a good trade-off between natural languages, which are ambiguous, and mathematical notation that can be hard to formalize for someone that is not an expert. The tool Fret provides support to the FRETish language, and it can automatically generate metric temporal logic formula from FRETish requirements. And these formulas can be fed to formal methods tools such as model checker, simulation, and verification tools. The problem is that we have to ensure that the formula that is generated preserve the semantic of the initial requirements, because this is particularly important for safety critical systems. Our solution to this problem was to formalize FRETish, its semantics, and the algorithm that converts a FRETish requirement to a formula in the PBS theorem prover and prove that the algorithm is correct. So to give you an idea of how a FRETish requirement look like, consider this natural language requirement for a detect and avoid system that says that while in flight, a warning alert must be raised within 3 seconds of entering the warning hazard zone of an intruder, which is defined as 250 feet horizontal and 50 feet vertical. This requirement can be expressed in FRETish as follows. We will have the scope, which is in flight, the condition, that is when horizontal distance is less or equal than 250 and vertical distance is less or equal than 50. What the aircraft shall, when within 3 seconds, which is the timing, satisfy the warning alert, which is our response. So in general, a FRETish requirement is composed by 4 fields and is characterized by these 4 fields that are scope, condition, timing, and response. The scope field defines the scope intervals in which the temporal requirement must hold with respect to a given mode, which can be flight, for example. For instance, we can ask the timing requirement to hold in mode. So while a mode is true, not in mode. So for example, while a mode is not satisfied, after or before mode, and so on. The condition field defines the triggers inside the scope interval. So since the condition is an optional field, if it is not defined or it is true, we have that the trigger is the beginning of our scope interval. So the requirement is required to hold since the beginning of the interval. Otherwise, the set of triggers is defined as the indexes when the condition becomes true from being false previously. In this example, here we have a trace row in an interval I, and the set of triggers is composed by the 2 indexes T3 and T6, which is when condition becomes true from being false at the previous time instance. And a special case is when the condition is never satisfied. In this case, the set of triggers is empty and the requirements holds trivially. The timing field finally defines the intervals in a trace that satisfy the timing requirement. For example, we have the timing within 3 that requires the result to hold within 3 seconds or time instance from the trigger. In this example, we have the interval I1, which satisfies the timing requirement because the trigger and the result hold at T1. And then we have the interval I2, which does not satisfy the timing requirement because result is never true, but we have a trigger at T5. The semantics of a timing requirement collects all the intervals that satisfy these timing requirement in a trace. So in this case, it's composed by the interval I1. In FRETish, we have several timing available, such as immediately, next, never, eventually, always, and so on. Finally, we can define the semantics of a FRETish requirements as the set of traces that satisfy the timing field in each scope interval in a trace defined by a scope field. As I mentioned in the introduction, the FRET open source require elicitation tool provides support for the FRETish language. So it provides a graphical user interface where the user can input the requirement and provides also an automatic translation from FRETish to future and past time metric temporal logic. In this work, we focused on the past time fragment of MTL, which is an extension of the linear temporal logic where each temporal operator is augmented with timing constraint that can modify its scope. In the past time MTL, we will have the past time operators such as previous, once, historically, and since. And a trace, it's in the semantic of a formula. So a trace models a formula if the formula holds at the end of the trace row, since we are talking about past time linear temporal logic. So the algorithm that produces a temporal logic from a FRETish requirement is compositional on the requirement field. So the first thing it does is to characterize the scope interval endpoints that are left and right. And this depends on the scope. So in our example that we see before, we have the scope in flight. So the interval left point is characterized by this formula that says that either flight holds at the beginning of the interval, or it does not hold at the previous time instant, but it holds in this time instance. And the right hand point is characterized by this other formula that says that flight does not hold, but it will hold in the previous time instant. The formula associated to triggers and conditions are the following. We define the function trigger as this function that returns this formula that is true each time condition becomes true from being false at the previous time instant, or if the condition holds at the beginning of the scope interval. So condition and left holds at the same time. The situation in which no trigger is true inside an interval is characterized by this other formula, no triggers, that says that since and including the instant where the v left is true, condition does not hold. The formula associated to timing is called core formula, and it models the behavior of the timing field. For example, in the case of always, we have this formula that is satisfied when no triggers is satisfied, and this is when the requirement holds trivially, or the result is true since and including the time where the trigger is true. The core formula can be interpreted in a generic finite interval, which is defined by the two endpoints left and right that we defined before. And this formula is called base formula and depends just on the timing. So what it does is imposing at each point in the scope interval the core formula for all the timing except for the eventually timing, where the core formula is imposed just once. And in addition, this base formula can be imposed for each scope interval in a trace. And the final formula is called general formula, and is the formula that is associated to the entire requirement. So we have the base formula that works at the level of a single interval, and the general formula that works at the level of the trace. So each interval in a trace. So for proving that this general formula is correct, we have to consider that we have 8 different scopes, 2 possibilities for the condition if we specify it or not, and 10 options for the timing. For example, we have eventually, always, immediately, etc. This is a total of 160 combinations. And of course, proving each combination and that the formula associated to each of these combinations is correct is not a very clever idea. So we structure the proof to be compositional as the algorithm. So we have one lemma for each possible condition, timing, and scope option. And these amount to a total of 20 lemmas, plus additional auxiliary lemma that we needed to prove these main lemmas. And in this way, we have an easy to extend proof framework. So every time a new timing or scope is added to FRETish, so the FRETish language is expanded, just one lemma is needed to be added to our formalization. So what we have proven is that for every trace, every execution trace row and a scope interval I, such that the left point of I are field left and field right. If an index T is a trigger, then the trace at time T satisfy the formula trigger, and vice versa. And if no triggers exist in the interval, then the formula no trigger is satisfied, and vice versa. Then we show that an interval belongs to the semantic of a timing constraint if and only if the base formula produced by that timing is satisfied in the trace in the right-hand point of the interval. So at the end of the scope interval, the base formula associated to the timing is satisfied. And finally, we have proven that if a trace belongs to the semantic of a FRETish requirement, then this trace is also model of the general formula computed by FRET for that requirement, and vice versa. So we have 3 levels here of compositionality. We have the part of the condition, the part of the timing, which is proven by cases on the 10 timing that we have, and the requirement level, which is proven by cases on the different scope field that we can have. So to conclude, we have defined a compositional and extensible proof framework for the FRETish language, and we have proven that the formula generation implemented in FRET is correct. And this proof effort was useful because we have discovered, in fact, 2 oversights in the algorithm of FRET. And we also found some ambiguities in the graphical user interface semantic visualization tool in FRET. So it was actually useful to improve the tool. In addition, we have learned that this rigorous formalization in combination with the previously done testing framework that was done during the development of FRET was a good strategy. In fact, testing was very valuable at the beginning of the development of FRET to find errors early on. However, of course, testing is not proving, and proving added additional guarantees to the FRETish language and FRET tool. It added the coverage of all possible corner cases, and this is very important, especially if we want to use FRETish for safety critical systems. So in the future, We plan to extend our formalization to also the future fragment of the MTL logic. We want to add supports for infinite traces. And also, we would like to continue to support any further extension of the FRETish language. So that was all. Thank you for your attention.